Welcome to Wave Properties 3, and we're going to look a little more closely at something called the group velocity. And you can see the first equation that I've written actually comes from some problems that we did. It's the sum of two cosines here and over there. They're slightly shifted in frequency. So this wave here has a slightly higher frequency shifted by delta omega. So in fact, what we have here is that delta omega is much smaller than omega, so that the waves are sitting around omega and k plus or minus a little bit. And so this is the higher frequency wave, and the other is the lower frequency wave. So there, you can think of this as two tones that are slightly higher and lower. If you play them together, you'll get what's called beats. You know, wah, 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 something like that. Now, what we can do to understand this better is to use a trigonometric identity to combine these. And if we do that, we get twice the cosine kx minus omega t. So that is a high frequency wave, so let's draw it. High frequency. And now over here, we need to multiply by what's left in this identity, which is going to be cosine of delta kx minus delta omega t. And this is a low frequency. And so if we multiply the two together, this will sit as an envelope, kind of a package over top of this. And the wave will look something like this. It'll have so we have a high frequency wave that's amplitude modulated by a low frequency wave. Now, to get a better understanding of what this means, I have an example of this. The values aren't sine waves or cosine waves. But let's see how this actually works in terms of a high frequency wave that has a low frequency wave as an envelope. We can see it in the following video. Here's an example. You can see it's taken out of Wikipedia, and the person who did the video, his name, it's under www.bcarlson.com. So he did this video, and what you see is a little packet of waves, and the wave packet is moving a lot slower than the actual jiggly wiggly waves inside the packet. So the low frequency envelope has a lower group velocity than the phase velocity of the individual high frequency oscillations inside the envelope. So that often happens where the phase velocity is faster than the group velocity. Now let's consider an example for a prism where we actually see the effect of this. You can look at Wikipedia for the properties of a prism. And we know that a prism breaks apart white light. So what we're going to do is start with the phase velocity of the prism and then compute the group velocity. So let's do that. We know that for a prism, the phase is equal to speed of light divided by the index of refraction. Now, wait a minute though. We know that a prism breaks white light into its components, so the index of refraction depends on the frequency, so we'll have this. So the phase velocity, classic for a piece of glass, a prism, and it's omega over k as we saw previously. Now, what we need to do is to calculate simply d omega dk. Is there a problem with this? Is it easy to calculate d omega dk? I've not told you what the functional form of n of omega is, so we're kind of stuck. There's a trick here in a lot of books in electromagnetics because it often happens that formulas are like this. So let's write K in terms of omega. So that's easy. We just rearrange this formula. So K is equal to omega times n of omega divided by C. So we can easily calculate, we don't have to know what n is, but we can calculate dk d omega. So the question is this: if we can calculate dk d omega easily, that's easy. It's easy. I mean, it's just simple algebra, as you can see from the form of k, but how do you get d omega dk from that? Well, they turn out to be reciprocals, and that's something that you can check in lots of different calculus books. It's like if you have a simple straight line, y equals mx, the slope is m. But if you look, what's the slope if x is equal to y over m? It's the reciprocal. Same idea. So we just have to calculate dk d omega and take its reciprocal. So that's all there is now. D omega dk is equal to the group velocity in this case, which is dk d omega, reciprocal of that. So that's very easy to do now. We just do the derivative. So differentiate this with respect to omega and make it to the -1. So we have a product in the top. That's a constant. So we put 1 over c. And now we differentiate. So derivative of omega, use the product rule, is just 1. So it's n of omega plus omega dn by d omega. So now we can easily take the reciprocal of that, and it's equal to c divided by n of omega plus omega dn by d omega. So that's the group velocity of the light waves going through the prism. What's important about the group velocity, as you saw from the videos, that is the speed of the packet. So it's the speed of energy travel, not the little wiggles. The energy is associated with the packet. In some of the optics literature, this has a special name. N of omega plus omega dn by omega is called c divided by ng for the group. So it has an analogous form to the phase velocity c over n, group velocity c over ng, given by that. And that's a straightforward example, but really encapsulates the basics of calculating the group velocity. And you can see the pictures in Wikipedia, the light refracted and bent out as it comes out of a prism. By the way, this is clearly a wonderful way of looking at light.